For decades, science textbooks described the edge of our solar system as a quiet, cold transition zone, a place where the chaotic energy of the sun gently faded out into a peaceful, uniform vacuum. To take a closer look at our neighboring planets, NASA launched Voyager 1 in 1977. It was designed for a simple, limited mission: fly past Jupiter and Saturn, gather some data, and shut down after 5 years. The engineers who built this spacecraft were working in a pre-digital era. They calculated orbital mechanics and interstellar trajectories using slide rules and paper, equipping the probe with less operating memory than a modern smart bulb. By all logical metrics, this machine should have died somewhere past the gas giants. Instead, it kept accelerating, using gravitational slingshots to reach the outer limit of the sun's influence, the first time any human-made object had ventured into the environment that lay beyond. In 2012, Voyager 1 crossed the heliopause. This is the precise boundary where the solar wind, the constant stream of charged particles pouring off our sun, finally runs out of energy and the true void between stars begins. This temperature plot shows exactly what happened when the probe crossed that line. Instead of the flat, freezing baseline everyone predicted, the line violently spikes upward. Voyager found a wall of fire, detecting charged particles colliding at nearly the speed of light and generating temperatures approaching 54,000 degrees Fahrenheit. Looking at this shifted diagram, we can see another anomaly: magnetic reconnection. The solar magnetic field lines and the galactic field lines were supposed to remain completely separate. But as these vectors indicate, they actually snap together and release massive bursts of energy into the dark. These discoveries revealed an environment of high-energy collisions and magnetic chaos. The frontier was more dynamic than any theoretical model had predicted, proving that the space between stars is far from empty. Since 2017, deep inside the interstellar medium, Voyager's instruments have been picking up a continuous, persistent emission. It is a steady hum in the local plasma that existing physics models cannot explain. This structure stretches over 930 million miles. The signal's consistency proves Voyager is moving through a massive anomaly, not a glitch. As this scale transforms into a topographic wave map, plasma density visibly ripples. Interstellar space holds invisible architectures of shifting charged particles. Interstellar space has a geography, and it has weather. For the first time, we are mapping the actual turbulence of that environment in real time. Capturing this data requires a fragile observer. In 2023, after nearly 50 years of exposure to deep space radiation, a single energetic particle slammed into a memory chip inside Voyager's flight data system, fracturing it and corrupting the spacecraft's entire transmission. Modern software engineers were forced to sit down and figure out how to remotely rebuild the operating logic of a broken computer using programming languages developed in the 1970s. They had to execute this fix across a 15 billion-mile gap. Every single command or line of code required a 22-hour journey out and another 22-hour wait for the spacecraft's response to crawl back to Earth. Our only access to this environment relies on a small team of engineers working to keep a 50-year-old machine functional across 15 billion miles. This diagram shows why mapping that distant turbulence matters to us locally. The heliosphere is the protective bubble shielding Earth from cosmic radiation. As shifting waves of interstellar plasma push against it, we can see that our shield is being warped and distorted by external forces we are only just beginning to track. Zooming out from the solar system to this line graph, we see a more immediate problem. Voyager is slowly dying. Its internal plutonium power source loses about 4 watts of output every year. This has already forced NASA to shut down critical scientific instruments, and the power level will hit a terminal threshold in the early 2030s. Engineers are currently attempting an experimental procedure they call the Big Bang. The goal is to reroute power distribution to squeeze just a few extra months of life out of the remaining sensors. Despite these efforts, the physics of a decaying power source are absolute. The real-time map of the void will soon stop being drawn, and the only window we have into this environment is physically closing. No replacement probe is currently funded or waiting to be launched. Once Voyager finally powers down, humanity will enter a 30-year blackout with no instrument in place to monitor the environment outside our solar system. After the instruments go cold, the machine will continue coasting blindly into the darkness at 38,000 miles per hour. Bolted to its side is the golden record, a copper disc carrying the sounds and scientific diagrams of Earth, continuing its physical journey long after the engineers who saved it are gone. The universe has proven to be larger and more active than our early equations allowed for. The signal is still faintly trickling in, leaving us with a question: whether we intend to be the kind of species that builds another machine to listen.